Okay, so we will continue with the oblique shock discussion. We will so if I have an oblique shock like this and the velocity v1, so the shock angle is beta and the velocity is deflected like this. So, this would be my deflection angle. The normal velocity before the shock is this, which is v1n, and the tangential component is this v1t, and we have also seen that v1t is same as v2t. So, this this is v2, this is theta, this is v1 v2t, and this is v2n. So, this angle is beta minus theta. Okay. This angle is beta is the shock angle, the angle between the velocity v1 and the shock, and theta is the deflection angle because it is deflected by theta degree. The velocity, the resultant velocity is deflected by theta degree. So, this is deflection angle or the turn angle because it is turned by theta degrees. And from the velocity triangle, we get v1n to be v1 sin beta, v2n to be v2 sin beta minus theta, and v1 t is v1 cos beta, v2 t is v2 cos beta minus theta. Okay, so if you take this angle sine of beta and sine of beta by 2 and cos of beta and cos of beta minus 2, you would get these components. We also know that v1t is v2t, and hence we can write v1 cos beta as v2 cos beta minus theta. And we have also seen m1t is nothing but v1t by a1, which is m1 into cos beta. m2t is v2t by a2, which is which is m2 into cos beta minus theta. Likewise, your m1n, so the Mach number based on velocity, normal velocity before the shock is this. So, this would be m1 into sin beta, m2n is v2n by a2, which is m2 into sin beta minus theta. Okay. So, those are the components of Mach number based on your components of velocity. So, for a normal shock, I can write P2 by P1 as 1 plus gamma m1 square divided by 1 plus gamma m2 square, or I can also write this as 2 m1 m square by gamma plus 1 minus gamma minus 1 by gamma plus 1. If I substitute, m2 square equals m1 square into 2 by gamma plus 1 m1 plus divided by 2 gamma by gamma minus 1 m1 square minus 1. So, where m2 and m1 are the Mach numbers before and after the shock. So, in this equation, if I substitute m2 in terms of m1, I would end up with a relation that is like this. So, your pressure before and after the shock in a normal shock is this. But here, if I draw this in a normal shock, what I have here is V1n and V2n, and for normal shock, our components V2 equals V1t equals V2t equals 0, and your V1 is V1n and V2 is V2n. So, you could assume a oblique shock with V1n and V2n as your velocities across an equivalent normal shock. Okay. So, if I have my V1n, I can get shock relation to get V2n. So, if I have my M1n, I can get an equivalent this thing. So, instead what I would do is I will replace M1 with M1n, M2 with M2n, and I get my shock relations across my now use normal shock relations to get the Mach numbers before and after this. So, this equation which I have here, so this is 1, this is 2, I can relate m2n square equals m1n square plus 2 by gamma plus 1 divided by 2 gamma by gamma minus 1 and m1n square minus 1. Okay. Likewise, my P2 by P1 also can be related to my normal component. Okay. So, if I know my normal component of the velocity, I can get the Mach number based on the normal component. I get the pressure relation related to that, or my Mach number after the normal component of the velocity after the shock. And if I get that, once I get m2, I can substitute in this equation m to n, which is related to m2 and this thing beta and theta, and this also in beta and theta. I can find theta and beta essentially. Okay. So, the idea is, if I have m1 and beta, I can compute my m1n. If I know my m1n, I can get my m2n from shock relation. If I know m2n, I can find my theta or m2 and theta. Okay. We will see how we can do this. by getting a relation between m, theta and beta. Okay. So, that is our next exercise. We will try to derive something called theta beta m relation. So, I would my tan beta is 1 by n by V1 t from these triangles. So, I get V1n by V2n is tan beta. Likewise, tan beta minus theta is this thing V2n divided by V1t. So, if I divide these two, tan beta minus theta divided by tan beta is V2n by V1n, which is also my rho 1 by rho 2 from the continuity equation, which we have seen some classes previously from previous lectures on continuity equation around the oblique shock. So, rho 1 by rho 2 across the shock is rho 2 by rho 1 across the normal shock is m1 square divided by 2 plus gamma minus 1 m1 square for normal shock. Okay. I use this relation and replace m1 with m1n. So, my rho 2 by rho 1 is gamma plus 1 divided by m1n square divided by 2 plus gamma minus 1 m1n square, and m1n is nothing but gamma plus 1 m1n is nothing but m1 sin beta divided by 2 plus gamma minus 1 m1 sin beta the whole square. So, if I substitute this here, I would get tan beta minus theta divided by tan beta equals gamma plus 1 into m1 sin beta the whole square divided by 2 plus gamma minus 1 into m1 sin beta the whole square. So, we will reduce this equation. So, this equation is relation between theta, beta and m1. We will reduce this equation further, but this in this equation it is just beta, theta, gamma and m. There is nothing that is So, I can reduce that equation to this is rho 2 by rho 1. What I have here is rho 1 by rho 2. So, this should be the inverse of that. So, this will be tan beta by beta minus theta. Okay. So, this is rho 2 by rho 1, this is rho 1 by rho 2. So, I have to take the inverse of that. Okay. So, if I use the trigonometric relation, theta and you reduce this further, I can get a relation like this. Okay. So, I take this relation divided by tan theta into 1 by tan theta, and I reduce that to this particular form, and this is what we have right now here as my say, let us take this as A. So, my tan theta is essentially 1 minus A into tan beta divided by 1 plus tan square beta into A. So, I substitute A from this relation, which is the inverse of this, which is 1 by A, which equals 1 by A. So, I substitute this quantity there, I would get this relation, okay, which I can modify to get this form, 2 cot beta into m1 square sin square beta minus 1 divided by m1 square gamma plus cos 2 beta plus 2. Okay. I will write that equation here again. So, I get a relation of tan theta in beta and m alone, which would be 2 cot beta into m1 square sin square beta minus 1 divided by m1 square gamma plus cos 2 beta plus 2 and this. So, this is our so called theta beta relation. Okay. For a given theta and m, find your beta is the problem. So, if I know my beta and m1, I can get a theta, or if I know my theta and m, I can get a beta. Okay. So, now if you look at this equation, theta is 0 if cot beta is 0 or m1 square sin square beta equals 1. Okay. Or your theta is 0 when beta is 0 or your beta is 1 by sin inverse 1 by m1, which is also your Mach angle. So, you have no deflection. So, deflection angle is 0 when beta is 0 or Mach angle is your beta is same as your Mach angle. So, the theta theta is the velocity with the angle at which the velocity is deflected. Okay. So, this deflection is 0 if beta is 0. So, beta is 0 means beta is 90 pi by 2. Beta is pi by 2. Okay. So, when beta is pi by 2, you have no deflection, or when beta is equal to a Mach angle, there is no deflection, which means if I have a normal shock, my beta equals pi by 2. So, when I have a normal shock, there is no deflection in my velocity component. So, the theta is 0 in this case, okay, for a normal shock. Or when I have a shock angle which is same as my Mach angle, then again I have no deflection in my velocity component. Okay. So, if I have a shock angle between these two, somewhere like this, something like this, I have a shock angle. So, this is Mach wave, this is oblique shock. Okay. So, all your oblique shock is between the normal shock solution and the Mach solution. So, if I have a wedge like this, the Mach angle may be something like this, and the normal shock is something like this. So, all your oblique shock solution lies between these two values. Okay. Between your shock angle and the this thing. So, all your theta values should be within this. If my theta is some finite value. Okay. Now, another inference that you obtain from this plot or this equation is from a plot of theta and beta for a given m. So, I have my theta here, which is my deflection angle, beta is the shock angle. Okay. Let us consider m1 to be 2. So, for a given m1, for various theta, how will the beta change is what I am going to plot. First is beta equals pi by 2, there is no theta, and when beta equals mu, which is sin inverse 1 by 2, which is your m1, which is 30. I have theta equals 0. Okay. For theta equals 0, for M1 I have a shock angle 30 degrees or pi by 2. So, this is my normal shock solution, this is my Mach angle solution, okay, for a Mach number of 2. Now, if I change my theta, so if I change my theta, theta is something else, I can compute my beta, and I will see that that will look something like this. So, if I change my beta for M1 equals 2, I would get 2 betas. If I change to another theta, again I would get 2 different beta. So, what does this mean? I have a deflection here from by a plate that is kept at an angle. So, the flow is this way. Okay. The flow comes and there is an oblique shock here, and the flow gets deflected by theta degrees, and this is my beta. So, I have a shock angle beta because of this deflection. The streamlines have to be deflected this way. So, this angle is my theta. Okay. Now, this theta can be one of these two is what it says. So, for a M1 of M1 equals 2, for this particular deflection angle theta, I can have 2 betas. Okay. It would be either this or this. So, it could be either this or another value here. So, if I call this as beta 1, this could be beta 2. Okay. So, there would be 2 shock angles possible. So, to draw this little more neatly, this would be this would be this. So, this is first shock beta 1, this is the second shock beta 2. Okay. So, it's the first, this is the first solution, this is the second solution. So, this would be my first solution, this would be my second solution. So, for a given theta and M1, I can have 2 betas. That is what you get from this equation, which is the which is plotted here. So, if you write a program which can input M1 and theta, it will compute 2 values of beta. Okay. So, the if you know beta, I can find my M2n, which is M2n is M2 by sin beta minus theta. So, if I know my M1n, I can use a shock angle to shock relation, normal shock relation to get my M2n and compute my M2 from this particular relation. Okay. So, essentially I have 2 solutions, one is this one is this one. Okay. So, this particular one is called the weak solution, this is called the strong solution or strong shock. So, this is my strong shock, this is my weak shock. Strong shock, weak shock. So, in a strong shock, the Mach number after the shock is less than 1. In a weak shock, the solution, the Mach number after the shock is can be supersonic. It is supersonic. So, which one is selected depends on the so called back pressure. So, the pressure available here will decide whether the shock should be weak or strong. Okay. So, depending on the back pressure, one of these solutions would be picked by the flow. Okay. Or I will write here, strong or weak shock depends on your back pressure, but it has to be one of these two. It is either this angle or this angle, nothing in between. Okay. Now, if I keep increasing my theta, so I keep increasing my theta, there is a limit to which I can get these solutions. So, the maximum theta that is possible is my theta max. Okay. So, theta max is nothing but for the given m1, how far I can go to get a solution, get a beta from this solution, from this equation. Okay. So, that equation gives me a beta, and that, so the maximum theta that I can go to get a solution from this equation is the theta max. That is also the angle at which when these two solutions are 1. Okay. So, that is my theta max, and I can also find theta for which, or beta for which my m2 equals 1. So, what I do is I take that relation m2 square equals m1 square square plus 2 by gamma minus 1 divided by 2 gamma by gamma minus 1 m1 square minus 1. So, I substitute this would be n, substitute the appropriate number for what would be the beta, that would give me m2 equals 1 condition here. Okay. So, there will be some beta which would give me equals 1. So, I have a theta max, and I can also get this condition where my m2 is equal to 1. So, if I draw it for different Mach numbers, it may look something like this. Okay. Now, I can find the limit of this. I will draw this here. So, this is okay. Tending to infinity, I have a limiting value. So, this is for m1 equals 2, this is for m1 equals 1 point something, this is for higher values, this is increasing m. Okay. So, I can get the tangent of this theta max for different m1. If I connect, if I take the locus of those points of theta max, I would get a line like this. So, this is my theta max line. Likewise, I can compute, I can get the angle at which beta at which you get m2 equals 1, that would be my sonic line. It would be here, limit m1 tending to 0 tan theta, and find the theta max for this. So, I can tending to infinity. So, in the limit m1 tending to infinity, how will the theta vary is something which you can compute from this. So, if m1 is infinity, then I would have a curve, and I can also find the theta max for that particular case where m1 tending to infinity. So, theta max would also result in a limiting value, which will look something like this. It goes from here and it goes. You can find this value theta max at m1 as m1 tending to infinity. So, all these things you can get it from this particular equation. So, the point is, if I have a oblique shock, say for example, I have a shock here, this is my theta and this is my beta, this is my m1. Okay. What I can do is I can find my m1n, because I know one of this. So, let us assume that we know theta. So, this is a fabricated ramp. Okay. So, I am given theta and I am given m1. So, from this relation theta m1 I know, from which I can find beta from theta beta relation, from theta beta m relation I know beta. The moment I know beta, I can find m1n. m1n is nothing but this m1 divided by sin beta. Okay. So, if I have a ramp, the theta is given, m1 is given. So, from theta and m1 using theta beta m relation, I get the beta. The moment I get the beta, I can find m1n. m1n is nothing but m1 by sin beta. m1 is okay. m1 sin beta, correct, m1 sin beta. The moment I get m1n, I can get m2n from normal shock relation. The moment I get m2n, I can get m2, which is m2n divided by sin beta minus theta. Okay. So, if I have a wedge, if I have a ramp like this or a wedge like this, which so this angle theta which is facing the flow B1. So, I know my M1. The moment I know my M1 and theta, I can get the shock angle beta from theta beta curve. The moment I know my beta, I can find the M1n. The moment I know my M1n, I can find M2n from normal shock relation. Once I know my M2n, I can find my M2. So, if I know the Mach numbers before and after the shock, I can literally find everything. We know all the quantities across the shock for P0 y, P0 x by P0 y or P0 1 by P0 2. All those things you can actually find it across the shock if we know the Mach numbers. Essentially, that is what we need to do. Once the flow encounters an oblique shock, how will the property change, and how are we going to use the normal shock relations to find the properties after the shock. Okay. Okay, thank you. We will do the problems next class.